Greetings. Welcome back. What did we learn? We learned something about conceptual design, something graphic, something pictorial, something that could be a common discussion point between a designer who knows technical stuff and basically the customer, the client, that only expresses the needs. So that was something of a pictorial, a graphical. It was used to introduce the entities, the relationship, and attributes. Now, the next stage that we want to do, we would like to go into a little bit of a detail to the next level of detail where we are going to replace conceptual design with table, spreadsheets, and the operations that we want to do on them. Let me share my screen with you. So that is this is lecture 3, a relatively long one, and I would like to rearrange some of the parts so that we maintain continuity in our discussion. What did we discuss? We discussed the database design terminology and importance of it, discussed requirements and the conceptual design, and we went over the basic and advanced constructs of entity relation modeling and how it helps to communicate between the designer and the client. What we want to do, we want to slowly talk about the table that is going to replace our graphical representation, pictorial representation. So the way I'm going to do it, I'm going to go first talk about a little bit about the spreadsheet and the table and some of the understanding that we need to carry with us as we move to the next part. Then I'm going to convert the ER diagram to tables so that we know what it means to us. Then I'm going to go and talk about the decompositions, especially normalization. But then I'm going to come back and talk about operation, algebraic operation, relational algebra. And there we are going to talk about multiple operations that we have. So let's begin on part 1. In part 1, we spoke of relational model. Basically, we had a bunch of entities and that were supposed to be related to each other one way or another, perhaps on the actions that they take upon each other within an organization, within a whole system. And what we talked about is that these actions, each one of them, each of those collections of attributes and entities could potentially translate to a spreadsheet. So let's take a look at the spreadsheet. This is one example. So remember, we had a case where, for example, we talked about customers, customer phone number, email, address, first name, last name, and possibly you could potentially have even preferences, bills and balance and things like that. And then we had the store talking about the movies, different types of movies, multiple copy of the same movie, but movies with genre and different categories, drama, sci-fi, and everything else. And then we had in them, for example, actors and actresses and everything else. That was what we did in the conceptual design. Now we want to map that slowly onto the spreadsheet. But before we go, I want to just talk about one of these entities in a spreadsheet. So take a look at this spreadsheet. This is a kind of an Excel file. We call this a table, obvious, and we call this a relation. It has attributes. The first row is actually discusses the attributes, and attributes would be the column. So this is ID column, this is username, and this is the status. So that's going to be the attributes or the column of the table or relation. Then each of these are going to be called instances or rows and records or tuple. So that's this is what it is. Kind of a mathematical now. A little bit we go into the math along the way when we finish this lecture series. A relational database is a collection of relations that together describe a structure of interrelated data organized based on their relationship. Each relation will be structured as a table with a unique name and multiple rows, tuples, and columns, attributes. We are trying to actually establish the terminology that we would be using. So in the future, when we talk about, for example, attribute, you should automatically consider that as a column. When we say, give me a row, give me a tuple, it means give me an instance, give me an example, give me the possibility that could be fitting in that area. The arrangement of the columns and rows in a relationship is not really important. You could potentially have these two switched over, swapped. You could have username here and then ID here. You can potentially switch them over, doesn't matter. In the rows, it really doesn't matter how you're going to put them. You can put them one after another. You could put Frank on top and Adam next. It really doesn't matter. That's the understanding. Every position in a tuple can only have single values. We will get to this important statement, especially when we talk about first normal form, 1.5, where no repetition is allowed. So every cell is supposed to have a single value. For example, if you take a look, it is called Adam. Although Adam is composed of A-D-A-M, as in letters, but from communication point of view, Adam is an atomic representation. It's not divisible anymore. If you want to have a meaning, and the meaning is going to be the name of the person is Adam. There is nothing else you can do. You can't say Adam is equal to Ad-am. That's not the way it is. It's just Adam. This is called atomic representation of the cell. But for example, if the username is Adam Cotter, it is a combination of first name and last name. This is not atomic because you could still separate them. By saying this is atomic, it means it's going to be unique and there is no more you can do. It's going to be single. All the rows in a relation should have at least a unique column that would identify a row from others. So that's understandable. A tuple is a sequence of values which is representing a relation between n values. A tuple of n values. This is actually mathematic expressions of this tuple or row or record. That's what we could eventually refer to. A relation is a set of tuples. Of course, I put them all together, I make a table, and this is a spreadsheet. So let's get used to this. An attribute domain is the set of all permissible values. Well, when we talk about first name, you don't want to, I might be wrong, but I don't think that there is a name on this planet called Jupiter as a human being, or Mars, or Pluto, or Sun. Those are dedicated to planets. So when we say, when you take a look at this, when we say name, it's going to be the potential name that could either be 8 billion names of existing names, but it could even stretch back to thousands of years ago, where all of the possible names have been collected together. So the attribute domain is a set of all permissible values for an attribute in a relationship. All attributes in a relation must have atomic domain, meaning that whatever you do, it's going to be pretty much unique. When you say 1, can you divide it anymore? When you say 2, can you make it even more? Divide it to sub items? No. When you say active, can you divide it to ac and then tif? No. It's just atomic. It's very much understood. An atomic domain is when all elements of the domains are indivisible. So we don't want to be able to divide them any further. Now, here is the challenge with the spreadsheet. The relatively rigid structure of the relationship is suitable for well-defined a static application, a stationary application, applications that don't change too often throughout the lifetime or lifespan. if you are going to see changes in the next hour, in the next minute, and that's going to happen, especially when you have text coming in, voice coming in, YouTube clips are coming in. That's going to be a whole set of challenge we need to solve. But what we are talking about is that you are going to have an organization in mind, and this organization is going to have something like order, Amazon order. Amazon order structure is not going to change rapidly from 1 hour to another. Yeah, they may have some sort of enhancement every now and then, maybe enhancement after 1 year or 2 years or something, but they are not going to be changing rapidly, such as minutes, second, hour. It is less suitable when data types and structures may change over time, especially when we say time. In this case, in our domain, we are talking about hour or day or week. We should be able to balance a trade-off between efficiency and predefined structures. So these are predefined structures. We don't want to, what we are trying to refer to right now is a predefined structure. A database schema is the logical structure of a database, which includes every relation schema in a database. So you can remember that there is going to be a relationship between all of these together, and that relationship, pictorially, we have seen it in the past. From a table point of view, we are going to see it again at the level of detail of a table. For example, this is a table. This is a relation. This is a table. I say a student. It could be a student. It could be a lecturer, the teacher. Then there is an ID, and the ID is going to be integer. One thing you need to note is that this seems to be incremental. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It's incremental. Make sense? And then you have the name, it's going to be a string. And then you have this department, again, it's going to be a string. And then the GPA is going to be float with 1 or 2 decimal points after the decimal points. Obviously, at some point, we want every basically tuple to be identifiable, distinguishable from other tuples in the table. We don't want to have the same row, Allen Mathematics 3.2, to be repeated. We will get to that, especially when we talk about 1NF in a moment. We need to have keys. So if you take a look at this table, let's go back to my table, this one. This table obviously has attributes, and we made it simple. It's just about 9 rows and about 4 columns. But imagine you may be dealing with millions of rows, and you could potentially be dealing with hundreds of columns, depending on how you collected the data and everything else. But this is a simplistic view of what we are trying to discuss. When you take a look at this, do you think the name Alan is unique? No. We may have Alan Carter. We may have Alan Milosevic, something like that. We may have a different name. The first name could be Alan Jr., Alan Sr. So the fact that Alan is could be potentially different people with different last names, or even inside the family with different prefix and postfix and everything else. That means Alan cannot tell me what that row is. If I say Alan, I can't say what that row is. Maybe in this table that is very simple, you might say, okay, there is no more Alan. But how do you know? Maybe the next time I'm going to add Alan here. And this time I'm going to talk about Alan Sr. or Alan Jr. or Alan Hubert. Okay, so that's what it is. So therefore, this is not going to be my key. This is not going to be even a candidate key. We talk about this in a moment. For every table or relation, you need to have key, and the key are potential candidate keys that could become nominated candidates for the key, and then you need to select. In this case, my best shot, for example, 3.2, you can't say 3.2 because 3.2 cannot identify the row to me. 3.2 could be related to Alan, 3.2 could be related to Kate. That's not helping. And the way it's going to be helpful is that simply say, this is the lecturer or a student table, and my key is ID. And as soon as I say tree, I know what that is. I know tree is Leah Astronomy GPA 4. Make sense? This is called key. By the logic of relational model, we must be able to distinguish each of the tuples in a relation. The attribute values of each tuple must be in a way that make the tuple uniquely identifiable. Uniquely identifiable. Superkey could a subset of attributes from a relation that uniquely identifies a tuple in a relationship. Now, if you take a look at this one, the example we just had a moment ago, perhaps my superkey might be ID. I could potentially say my superkey could be ID in conjunction with name. For example, I would say 2, Frank. Okay. I would even say 2, 3.8. Okay. I can do that. But in this case, absolutely ID is going to be my key. So keep that in mind. A subset of attributes from a relation that uniquely identifies a tuple in a relation. For example, the ID attribute of the student relation is a superkey, but the name by itself is not a superkey or even a key. Superkeys may contain more than one attribute, for example, ID and name. For example, if I ask you, do you have SSN number? Do you have SIN number? Do you have national ID wherever you are? That national ID for the government is the superkey. When someone said this is your SIN number or SSN number or national ID number, they will know everything about me. I have filled my census data and my form has been completed already. The government knows my education, my background, the tax I have paid, the salary I have received, everything by one single number, national ID. That's called a super key, and we will potentially call that primary key. Candidate key, obviously the name is indicative of what it is. Candidate key tells me, can you tell me, for example, potential keys? In the above example, you can't say Alan even is a candidate key. It's not. Alan who? And we have so many Alans across the globe in US and elsewhere. So that's not going to be even a candidate key for us. It's useless. But you could potentially say Alan Jr., whatever the state you are in, the city you are in, and the county you are in, and the state you are in, and the country you are in. That combination could potentially become a candidate key. Yes, a candidate key could be composite key. Composite key means it could be multiple columns, multiple attributes together. And that could potentially identify the tuple uniquely. So for example, if someone wants to find me, and I live in a city, Milan, in Italy, and they say Cameron, Milan, Italy, phone number, they can find me. They can find everything about me. And that's why people say don't leave too many information online, because they can potentially identify everything about you. If a relation consists of multiple attributes or sets of attributes that could uniquely identify each row of the relation, then we can refer to each of these attributes or sets of attributes, as I said, composite key, a candidate key. A super key, which none of its subsets is a super key itself, is a candidate key. That makes sense. Now, primary key, every table, every relation needs to have a primary key. That's the way you identify the rows of that table. So in the example above, ID number, a student ID 1234 is going to be the primary key. If it is a lecturer ID, that's a lecturer ID. If it is a university student ID, if it is a national ID, you could potentially say that these are primary key. Primary key is a candidate key that will be utilized in order to uniquely identify tuples. So now you may have candidate 1, candidate 2, candidate 3, and so on. You scratch your head and go, which one do I want to choose? You are a database designer. Which one do I want to choose to identify my tuples, my rows, uniquely? That becomes your primary key. A relation must always have a primary key, of course. The database designer chooses the primary keys for each relation. It's your job to define what the primary key is. It is a convention that primary key attributes be underlined in the schema. You could underline it, you could make it bold. Most of the time we make it bold, and sometimes we put an underline on we have a line under it to identify that this is a primary key. The primary key attribute values must be such that its value never or very rarely change. Numbers 1, 2, 3, 4. A student ID. Why do you want to change it? There is never going to be a change in your student ID or the staff ID or the national ID. When you got a national ID, you got a national ID. There may be extremely rare cases where the government decides to change your national ID simply because your national ID and all of the information you had have been compromised. You go, you place a form, explain, and you go through a process, and when it is approved, you change your national ID. So that would be very rare, extremely rare to do that. The most common type of primary key is auto-incremental keys, 1, 2, 3, 4, 5, which is an integer number that the database generates automatically. So we understand that. For example, if you take a look at this example that we have here, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And usually when you take a look at the primary key of, for example, as a phone number, you can realize that primary key is an indicative of the population of that city or that state or that country. So when you take a look at the country and the a number of digits in a phone number is, for example, 5. What does that mean? It means the maximum number you could have is 9999. Anything more than that is going to be, 999 and then 99. So that's the maximum you can go. And as soon as you have anything more, then that means you have to have 6, not 5. So usually the primary key is an indicative of how many people have been in that table, how many rows have been in that table. But sometimes for the sake of security, sometimes even with the limited number of people, maybe the ID that is assigned to you could potentially be 10 digits, although the population might be only 10. And that 10 digits is designed to be non-hackable ID. Now, when we go and break up the table, we need to understand that the broken table needs to refer to each other. So if this is the primary table and this is the secondary table, I'm going to say that this is the course that I'm teaching. This is the credit hours or whatever it is. And then this is the lecture ID, that's 3. And 3 means it's Kate Wilder. Okay, so this is when I break it up, when we go to 1 and F, 2 and F, 3 and F, I'm going to break up a larger table into a smaller table. And when I break it up into a smaller table, I have to maintain the relationship anyway. And the way I'm going to maintain the relationship is that I'm going to have something called foreign key, the residue of my broken table here in my primary table. So this is my primary table. Originally, this table and this one was together, but I broke it up. And when I broke it up, the primary table still maintains its own primary key anyway. But since you want to have a residue of broken table inside, you need to call this foreign key. It is a foreigner. It is something of a foreign nature to my primary table. And this is the foreign key is indeed a primary key of the broken table. So this 1, 2, 3 could be 3, 1, 2. So the 3 means Kate, 1 means Adam, and 2 means Frank. Okay. So foreign key is the mean by which two tables are actually going to refer to each other. A foreign key constraint indicates that for each foreign key value presented in a referencing relation, there must be a record in the reference relation where the primary key is equal to the foreign key value noted earlier. So this is primary key, and this is foreign key in the primary table, and this is the primary key in mine. Remember, in the lab, we discussed about constraints, and one of the constraints is that you do have to have the foreign key. So keep that in mind. A foreign key cannot be empty, so keep that in mind. We are going to talk to you in a moment about some of the issues when we have the join operation. Referential integrity. So one of the things we need to keep an eye on when we start breaking up the tables, we need to see whether the table is actually complete. Can you put them together and go back to the original one? So reversibility of your operation is very important. I'm going to repeat a number of terminologies that are very important that you need to keep in mind. One, no redundancy. We will talk about redundancy in a moment. No redundancy whatsoever of any kind. Okay, and when it is broken into pieces. The next thing is that whatever you do, it must be reversible. So when you break it up, you should be able to put them together and make it. It's like a puzzle. When you play a puzzle, what do? So you have pieces of the puzzle, and the pieces of the puzzles are broken around. You put them together, and the picture becomes complete. And if one piece of the puzzle is lost, your entire picture is lost. You're not going to have a proper, peaceful sleep at night, because your puzzle is not complete. So that's what it is. Referential integrity is about the consistency and accuracy of data within the relationship. We talk about that. Via a foreign key is one reason for the integrity. Foreign key referencing a primary key value, that has to happen. This requires data to remain consistent throughout the database. One of the issues with the integrity of the table, and again, it's something that has to come to you as a natural data designer, database designer. You need to be aware, you need to have an eye on whatever you do, and as soon as something happens, you need to be able to delete it. I'm going to explain a moment. For example, in this table, for example, number, this is a wrong one. So number 2 is actually Frank Clark, as in lecture ID. So if Frank Clark is removed, so there are some typos. It has been a long process to prepare these documents, these PowerPoints. There are some minor typos that we need to fix. As soon as I get alerted, I'll let you know. So when I say the 2 is gone, for example, Frank Clark has taken up a position in a different university and left our organization. As soon as 2 no longer exist, you cannot have in the primary table referencing to 2, because there is no Frank anymore. There is no Clark. Frank Clark has gone. If, for example, Kate Wilder has left the organization, then this has to be clear. Either the whole thing is going to fall off, this course will never be offered, or you're going to basically have this as 3, and as we discussed in the join operation, have it as in null, N-U-L-L, null, N-U-L-L. What does it mean? Yeah, we are going to offer CS 101, but at this time, we don't know who is going to be teaching it. It's going to be decided, to be announced, to be hired. If you say to be decided, to be announced, to be hired, and this course will be offered, then you're going to have 3 still in your secondary table, but here is going to be null, and here is going to be null. But the 3 altogether has gone. It means this has to be removed completely. Again, there is a bit of a typo. What does that mean? This is supposed to be the integrity of the database. As soon as I push something, I'm sure you have seen something called update. Update. So you do many things and everything else. You have worked with some of the softwares that you manipulate everything and say, can you please update? And then you can say update, and it's going to grab all of the pieces together, put them together, and give you one whole picture. If when you do update and your table cannot be formed properly, then you don't have consistency in your operation in breaking up the table. And the only way you can avoid that is to allow NULL and NULL here. If you don't want to, and if you want to remove the whole thing, then the whole referencing on number 3 has to be removed. Okay, otherwise it's not consistent. Adding a record to a related table without a valid reference record in the primary table is a no-no. So for example, if I say, here, this picture is actually very nice. So you take a look at the primary table, and then you're going to refer to 5. What do you mean by 5? There is 5, 5, 5, my 5. There is no 5. So when you say 5 and I say update, the program goes, there is no way it's going to update because there is no 5. You can't put 5 there. The only way you can do 5 is to say 5 here, and then say null, N-U-N-L-L, and then say null, N-U-L-L. That you can. Now, you have here Tom, and the last name is Physics, for example, right? You never used 4 in the past in any of your tables, not just this one. In all of your database, you have never used Tom Physics. Number 4. There, you're going to do something we call purge. You're going to purge this information, take it out, delete it, and therefore maintain consistency. As soon as you push update, everything like a Lego comes together, and you should be able to have everything in one picture. If you can, your database is consistent. If you cannot, your database is not consistent. Changing the primary keys in the primary table that would result in inconsistent records in the table. So if I change this primary, for example, if this was 5, I would have been fine. I'm okay. Of course, 2 hasn't been used here, so I don't see Frank Clark has been used here. Maybe it has been used in another table, so I can forgive that. But it has never been used, then you need to take it out, purge it. But if this is 5, then it would have been fine. But what happened to 4? Then you can either say I removed it, or you can say 4, and then you can say no, N-U-L-L, N-U-N-L-L. Removing records from the primary table when there are referencing records in the related table. So this is a related table, and you removed everything about number 2 in this table. Again, the assumption is there is no other primary table, and this is the only primary table you have in your database design. Then we are in trouble because you're never using 2, Frank Clark. And if you are not using it, then the database is not consistent. Purge the row, and then it becomes consistent. We talk about relational algebra in the next recording, but at this time, I think we are primed to talk about 1NF, 2NF, and 3NF. Stay tuned.